Hello, everybody. Welcome to the Audio Precision webinar. Today we'll be discussing the fundamentals of audio test. Our General Manager, Daniel Knighten, will be leading the conversation and be providing demonstrations in APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get underway. So first, please note that this session is being recorded. Secondly, we welcome questions during the event. So if you have a question for Daniel, you can submit it via the chat function in Microsoft Teams. And also, just as a side note, we will be sending a recording of this session to you within the next couple days. So be looking for that in your inbox as well. So Dan has a lot of info to share with you today. So without further ado, Dan, I turn it over to you.
All right, thank you very much, Paige, and good evening or good morning, or I guess good afternoon, depending on where in the world you're joining us from. But thank you for joining. Really, an hour is a little bit short to try and cover the fundamentals of audio test, but we'll do our best. And we'll begin by talking a little bit about what's special and unique about audio measurement, what makes it different from measuring essentially any other AC signal. We'll talk about common units of measurements. We'll go through different test signals that we'll experience when we make audio measurements. And then I'm going to dive into really just the first few audio measurements, but perhaps some of the most fundamental audio measurements. During the presentation, I'll pause every now and again to answer questions that you've submitted via chat to Paige. So let's start with what's special about audio test. Depending on your background, it may be unusual to think that there is specialized equipment required to make audio measurements. After all, why can't you just connect a microphone to a voltmeter and have an amplitude of an acoustic signal or measure an analog electrical signal directly? There are really three things that make audio measurement special. The first is a very wide amplitude range. If we're talking about voltage signals, the smallest signals we want to measure are the self noise of things like high performance analog to digital or digital to analog converters. And those are on the order of microvolts. And that scales all the way up to wanting to measure the output of the types of power amplifiers that are used to drive speakers for rock and roll stadium shows, which can exceed 200 volts RMS. So that's a very big challenge to have an analyzer that has a self noise of less than a microvolt and accepts the largest possible signal above 200 volts RMS. If we think about audio in terms of human hearing, generally accepted threshold of human hearing is 0 dBSPL. And the threshold of pain, so if you will, the maximum signal that humans can tolerate is greater than 120 dBSPL. So we're talking about a range of greater than 1,000,000 to 1. In terms of frequency, we often think of audio as being a low frequency application. After all, the bandwidth of human hearing is perhaps no more than 20 kilohertz. But humans register sounds from below 20 hertz, and perhaps some very young humans can hear things that are slightly above 20 kilohertz. That's over 10 octaves or 1,000 to 1 frequency range. If you think about typical spectrum analyzers, you generally analyze frequencies in the range of often the same octave. It's not very common that we look at signals over more than a 2-to-1 frequency range. And as a practical matter, particularly when we're testing equipment, we want to look at everything from the DC offset in A to D converters or power amplifiers, all the way to the out-of-band noise shaping products in switching amplifiers and converters. So often we're talking about a frequency range that goes from 0 hertz to well over a megahertz. As a practical matter, imagine a radio that could tune from AM into the microwave region. So again, this makes the equipment used for audio measurement somewhat unique compared to other pieces of common test equipment. And then finally, and actually perhaps the most challenging, we're much more concerned with the spectral purity of our test signals. One of the things that's remarkable about human hearing is that we are capable of discerning sounds that are well below the ambient noise floor. This room that I'm in talking right now has an ambient noise floor of 70 dB, but humans can actually, have somebody whisper from across the room and be able to understand that person. The human brain and the human auditory system is pretty incredible that way. And again, from a device perspective, high performance but not esoteric consumer devices these days are often in the range of 100 dB of dynamic range or residual distortion and noise. That's over 100,000 to 1 in terms of voltage range. And think about any digital circuit. Typically to work, they might need a signal to noise ratio of 6 dB or maybe 20 dB. But in audio, we often want to talk about not less, never even conceivably less than 40 dB, and maybe 60, 80, 90 dB is a benchmark for a high quality device today. And that's far above the dynamic range that you'll see in something like an oscilloscope. So as we talk about audio measurements, the most fundamental thing of all will be the units in which those measurements are expressed. So let's talk about some of the most common units and some of the most common gotchas or caveats to be aware of in those units. Depending on where you're coming to test and measurement from, probably the most common unit is either going to be volts or pascals. Starting with volts, the first thing I'd like to note is V by itself is ambiguous. If somebody says, I measured 2 volts, that by itself and without any context is not completely useful. In audio, we are most commonly talking about volts RMS, volts root mean square. This describes, if you will, the area under the curve or the average value of the AC signal. There's a term for this which I learned some time ago. The British used to call this the heating power of a signal. And what it meant was if you have a certain value of volts RMS and you connect that to a resistor, how much will it heat that resistor up? This is distinct from volts peak, which is the maximum instantaneous value of an AC signal. And finally, we distinguish that from volts DC, which is If we're looking at a DC signal, the only component, but very often we have AC signals or audio signals that are riding on top of a DC value. Humans cannot hear DC. If you will, human hearing is AC coupled, but we worry about DC offset or volts DC in the output of a device because in a speaker, it uses up travel or range in this speaker, and in a power amplifier, it means you will always be dissipating that amount of energy. So just to visualize what I'm talking about, if we quickly peek into our software, and I'll start by showing you an oscilloscope view. So this is a signal which is 1 volt RMS. And what you'll notice is the peak value of this signal is 1.41 volts. But if you will, the area under the sine wave is 1 volt. So that's where the 1 volt RMS comes from. Now, what you will sometimes see is volts peak to peak, which is literally from here to here, and that would just be twice the peak value, assuming it's a symmetric waveform. Now, and but just to cover it, a Pascal is a unit of sound pressure. So in SI terms, 1 Pascal equals 1 Newton, a unit of force, per meter square. So 1 Pascal is 1 Newton being applied over a square meter. Now, to give you some perspective, if you saw something that was pascals by itself, 1 PA, it is generally understood that when somebody says something like 1 Pascal, they probably mean 1 Pascal of sound pressure. But just like V by itself is ambiguous, it's useful to discern that, because depending on the background in which that unit is being expressed, they might literally just mean pressure, as in static pressure. And just for some comparison, 1 Pascal is a high but comfortable listening level. If you listen to 1 Pascal for more than 8 hours, you would probably have some permanent hearing loss, but unfortunately there are a lot of teenagers who like loud music. However, 1 Pascal of sound pressure is riding on top of approximately 100,000 pascals of static atmospheric air pressure. So one way to think about it is acoustic sound is a very small AC signal riding on top of a very large DC offset. And the only time humans can sense the static pressure is when we are congested and can't clear our ears. Otherwise, human hearing is AC coupled and we don't sense the static pressure. In the digital domain, unfortunately, things get a little complicated. So generally speaking, in the digital domain, the most common unit is called FS, and it stands for full scale. Now, people often think of FS as being an analog to volts, but it really isn't, and I'll explain why in a moment. The main issue is FS, which does not have a definition in the System International of Units. It's instead an industry convention, just something people have decided to use. The nearest definition is a 1 FS signal is the RMS amplitude of a sine wave whose peak reaches the maximum digital code in a pulse code modulating sampling system. This is a definition that comes from the Audio Engineering Society, Standard 17. The Audio Engineering Society has never defined a unit for the instantaneous amplitude of a system. There is no standard or accepted unit for example, a digital DC offset. In the absence of that, Audio Precision has invented its own unit, which we call D, and D is an instantaneous unit, and there is a straightforward relationship. A sine wave with an RMS amplitude of 1 FS will have a peak value of D, of 1D, in one of Audio Precision's analyzers. So to visualize that for a second. So here we're creating a sine wave which has an amplitude of 0 dBFS, or if you prefer 1 FS. And what you'll notice is the unit in our oscilloscope view, which provides the instantaneous time value of the waveform, peaks at 1D. So whereas with volts or pascals, the same underlying unit represents the signal both in its RMS or root mean square quantity or in its instantaneous value form. In the digital domain, we have two different units and they are not directly interchangeable. Now, this is a very quick review of the most fundamental units. What I will say is there is a rich world of units beyond these simple amplitude units. There are units that cover perceptual loudness, such as fons and sons. There are units for audio power, such as dBm and dBmo. And there are units that are used in specialized cases, such as where we want to describe the amplitude of a signal, but with the pauses that a human introduces as they speak removed. So there's a rich world of units that are used in audio measurement. We'll start just with the most basic. Now, we started by just describing the, I'll say, linear representation of these units, but something that is used all the time in audio measurements is to talk about things in dB or decibels. Okay, a decibel is a logarithmic unit, and it's exactly the same as saying percent or ratio. And very simply, if somebody said, oh, this is 100%, they could also say this is 6 decibels. And in that context, it's important to realize that practically, unless it's understood, something like 20 dB by itself has no meaning. Saying something like that is no more sensible than saying 42% by itself. Decibels only mean something when a reference is provided. So common decibel units in the world of audio, dBV. So this is dB relative to 1 volt RMS, dBu, which is relative to 0.7745 volts RMS, dBm. dBm is a little bit special. dBm is actually a unit of power. So this is dB relative to 1 milliwatt. One thing to be aware of is because in power dissipation we have an extra square function. That means that the logarithmic ratio is 10 log instead of 20 log. Now the other thing to be aware of with dBm is dBm comes from the days when analog electrical audio signals traversed 600 ohm terminated circuits. And so it expressed actual energy dissipated into 600 ohms. These days, there are very few analog electrical circuits that are actually terminated into 600 ohms, and the more appropriate unit to use is dBu. dBSPL is a unit of sound pressure, and it's dB relative to 20 micropascal, which is generally understood to be the threshold of human hearing. That is to say, a room that had 20 micropascals of ambient noise would be considered silent by the average human listener. dBFS is dB relative to full scale. So 0 dBFS is the largest amplitude sine wave that can be represented in a digital system. Now, rather than doing the logarithmic math in your head, there are some shortcuts. Plus or minus 6 dB is twice or half the reference value. Now, for people who want to be picky, the actual ratio is 6.02 dB. Plus or minus 10 dB is approximately plus or minus a third. And plus or minus 20 dB is 10 times or 1/10. Now these are for energy units, so dB volts. 6 dBV is 2 volts RMS. For watts, it's every 3 dB doubles, again because of that extra squaring function in V squared over I. So in terms of it, 1% of our reference value is equal to minus 40 dB. So this might be a good point to take a couple questions if any have come in, Paige.
Yes, I've got a few questions for you here, Dan. So the first one is, actually I'm going to combine two questions about an SPCL filter. So essentially the question is, when measuring SNR or dynamic range, this sometimes requires the use of an SPCL filter. Why is that?
That is a great question, and it's anticipating me by a couple slides, so I will answer that question in just a couple more slides.
Okay, great. Another question, how does out-of-band noise affect AP measurements?
That is, I'll say, beyond the scope of this presentation, but we do have some white papers on our website that talk about out-of-band measurement. So if you can capture that person's, the requester's email, we can catch up with them and address that question.
Okay, thank you, Dan.
Thank you.
And one other question for you here is, if Pascals aren't that useful on its own, what extra information do we add to match it to VRMS?
Oh, I misspoke to suggest that there's anything unuseful about pascals. Pascals are the preferred representation of signal amplitude when that signal is traveling in air. So volts is when we're representing an audio signal in the analog domain, an electrical signal. But as soon as we put that signal into a speaker, and that speaker turns that into sound pressure, we would represent that sound pressure in pascals. And pascals is, when it's expressed by itself, if you just see PA, usually means acoustic sound pressure, so an RMS value. But like volts, it's not a bad idea to clarify that if you print it, that, oh, we measured this and it was so many pascals of sound pressure. That's all I intended to convey there, but I don't want to deprecate or depreciate the value of pascals. Pascals is a fundamental unit, and if we're measuring acoustic signals, we will be making those measurements in pascals.
Thank you, Dan.
Okay. So the next thing I want to touch on for just a moment is Crest factor, and particularly for audio precision analyzers, signal generator level calibration. Crest factor by itself is pretty simple. Crest factor is the ratio of the peak value of a signal to the RMS level of a signal. So if we look at our friend, the sine wave, if I generate a sine wave of 1 volt RMS, you'll notice that these peaks are actually reaching 1.414 volts peak. And so I divide one by the other. The crest factor of a sine wave is 1.414 or 3 dB, or for those of you who remember high school geometry, it's the square root of 2. A couple things to understand. A sine wave has the lowest crest factor of any signal that has all its energy at one frequency. And I'll return to that point in a moment. A square wave has a crest factor of 1. And that is the maximum RMS value you could get out of a system. So for example, if I go here, and I'll turn off interpolation so that we can see the actual square wave, and for fun, I'll also DC couple it. So now here we're generating a square wave, and I'll explain a little bit, but here I'm generating a square wave that has a peak value of 1 volt. And you'll notice it also has an RMS value of 1 volt. So that has a crest factor of 1. So nothing is going to have a crest factor lower than that. Everything is going to have a factor higher than that. And a sine wave is the signal that has the lowest crest factor and has all of its energy at one frequency. Now, one reason that crest factor is important to understand, and this is a little bit of a diversion into exactly how audio precision signal generators work, but we generate signals based on the equivalent peak level of a sine wave. And so you might have noticed that when I set my generator to generate 1 volt RMS, I actually got a signal of 1.414 volts RMS. And that's because when I generate a signal in APX, it actually generates that signal at the equivalent peak level of a sine wave. So what we call that is we're sine peak calibrated. So you notice if I switch over to the sine wave waveform, it has the same peak value as our square wave, but since it is a sine wave, we now get an RMS value of 1. That can fool you at times when you generate signals that are not sine waves with APX. And we do have a blog post that talks about how you can make sure you set the signal generator level for the desired signal level when you're generating signals besides sine waves. So let's talk about test signals for a moment. So one thing that you'll experience or have experienced is that by far the most common test signal in audio measurement is a sine wave. They're not super pleasant to listen to, but they have several advantages. So if I look at our sine wave here, and here we're generating a perfectly clear sine wave. If we look at the spectrum of this signal, you'll notice that apart from the noise floor, all the energy is at that one frequency, at 1 kilohertz. And one very simple advantage from a test and measurement perspective is if we put this signal into our device under test, everything that comes out of our device under test that is not at 1 kilohertz is some undesirable product. It's distortion, it's noise, it's alias products, it's hum, whatever it is, it's not something we want. And by putting in that pure test signal, it makes it easy to figure out what everything else is. If we put in other test signals, it's not as easy to separate the test signal from the noise and distortion in the output of the device under test. Now, frankly, another thing is that the sine wave has been the benchmark for making audio measurements since we've been making audio measurements, since mankind has been making audio measurements. And it's very useful to make new measurements and compare them to old measurements. Now, there are techniques that let us make measurements beyond the sine wave. So particularly for characterizing acoustic devices, a very common test signal these days is a continuous sweep or a log chirp, or you may have heard it called an exponential sine sweep. So this is a sine wave, but we sweep it continuously in frequency. The main advantages of this is it lets us get a very fast frequency response. Instead of manually tuning the signal generator at each frequency and plotting those results measurement by measurement, we can get a fully characterized device in potentially under a second, but practically not more than a couple seconds. One disadvantage of this technique that comes from the mathematical algorithm that underlies it is there's no noise result. So we can capture the fundamental frequency response and we can capture the distortion of the device, but we don't capture the THD plus N. There's another approach. We're still going to test with a sine wave, but what if we tested with all the sine waves at the same time? So there is the multi-tone technique, and this is literally we generate a bunch of sine waves simultaneously and we play them simultaneously. And we can capture the frequency response, the distortion, and the noise response of a device. But the results are a little complicated because we're capturing not just the harmonic response, but the intermodulation response caused by playing all those signals simultaneously. So there is a noise and distortion result. Unfortunately, it is not directly comparable to the results we get from a single tone sine wave. Finally, because we have more than one tone, the crest factor is much higher. And one way of describing that is whereas in a single tone, all the energy in our waveform is at a single frequency. In a multi-tone, the energy is going to be divided into the different tones. Now, particularly for acoustic measurements, say measurements in a room, perhaps tuning the speakers installed in your living room, it's actually quite common to use noise, just random noise. And we have two varieties that we'll most commonly see in the audio measurement world, and that's white noise. And white noise has a flat spectra in an FFT analyzer, and it has equal energy per frequency. And then we have pink noise. And the main advantage of pink noise is if you actually look at noise measurements in the real world, the natural world does not have flat noise with frequency. The natural world is actually dominated by low frequency noise. And what you generally see is a curve where the energy is equal per octave. And if we're looking at on a spectrum analyzer, we'd see a decrease of energy approximating 6 dB per octave. Finally, all of these previous test signals that we've discussed are kind of undesirable to listen to. So nobody listens to sine waves for pleasure, or multi-tones, or chirps, or noise. Though oddly enough, some would argue that if you have to work in a test lab all day long, the white or pink noise is probably the most pleasant to listen to. But what about making measurements with actual speech or music? So one advantage of doing that is setting aside the fact that they could be more representational of the actual test signal you're trying to reproduce with your device. Many modern devices with active signal processing will filter out standing tones or noise, and it will be eliminated and you won't get a measurement. So now with modern FFT signal processing techniques, we can actually make measurements on devices using speech or music or noise, or actually any signal, generally speaking, as long as there is energy content in that signal across a broad range of frequencies. So just to give you a little taste, so of course, this is, and this may come a little cross loud. I'm going to try and share this across the web link. But this is, of course, our friend, the sine wave. Well, I'm not sure if that is working. Doing this seminar online is a little bit of a challenge. Actually, let me do this virtually. Here's a spectrum of white noise, and of course you can't see it's somewhat random, but as the averages come in, you'll see that contract to a even distribution with frequency. And then if we reset this to pink, you'll see the 6 dB per octave slope in the pink noise. And then just for some perspective, here's the actual acoustic noise in the room I'm presenting with. Now, of course, you can't see my speech, but if I stop talking for a moment, you can see the pink noise-like slope. And then just for fun, here is a continuous sweep. This is an actual response from a speaker. And you can see it is a sine wave if you zoom in, but this sine wave is actually varying in frequency with time in a continuous way. And we'll compare that to multitone. And let's just do that a little louder. And that's what the acquired waveform looks like. It looks a bit like noise, but if we look at the spectrum, here we can see the peaks of each individual tone within the test signal. Okay, before I move on, would it be appropriate to take a couple questions here?
Sure, Dan, I've got a couple questions for you here. So the first question is about square waves. So a square wave has a crest factor of 1 and a sine wave 1.41. How is the latter lower than the former?
Sure. So we'll just return to this picture again. So here's our sine wave, and the peak value is 1.414. The RMS value is 1 volt. So our crest factor is 1.414. So it's the peak value divided by the RMS value. Now, if we switch to generating a square wave, and just to take away a couple optical illusions, essentially we'll look at the uninterpolated value. You'll notice that this square wave has a peak value of 1.414, but now it has an RMS value of 1.414 as well. So 1.414 divided by 1.414 is 1. So again, it just comes down to the crest factor being the peak value divided by the RMS value of a waveform.
Thank you, Dan. Another question here. What do you mean when you say continuously swept in frequency with respect to log chirp?
Sure. That can be a little bit of a confusing concept. So let's just zoom in on the start of this waveform. So it might not immediately jump out at you, but here at 70 milliseconds, the frequency of the signal is lower than it is here at 140 milliseconds. You can see the distance between the sine waves is closing. The frequency is increasing. And what's interesting about a log chirp is that is increasing continuously. Every sample representing this waveform is at a different frequency than the previous one. So in the different types of sweeps, such as a classic step frequency sweep, the signal generator would actually dwell at each step, each fixed frequency for a period of time. It would be no different than if we generated a standing signal and manually incremented the frequency. In a log chirp or an exponential sine sweep, or sometimes it's called a Farina sweep, the frequency of the test signal is continuously changing. There's no 2 seconds or 1 second or even any 2 audio samples that have the same frequency. And the frequency is increasing. So it starts at low frequency and ends at high frequency. So if we zoom out and look at the other end of the sweep, you can see now it's gotten very, very short, but it's actually still increasing in frequency right to the end of the sweep. So that's the continuous nature, and it's a little bit difficult to wrap your mind around what does it mean to have a sine wave where the frequency changes continuously, but literally every audio sample is at a slightly higher frequency than the previous one, but it is still a sine wave. It still has a crest factor of 1.414. And at any instantaneous moment in time, all of the energy is at one frequency.
Okay. Dan, another question for you. Can AP capture negative 360 degrees phase shift? That's the first part of the question. The other part of the question is, does AP have the buffer data to know it is negative 360 degrees out of phase?
That's a little bit of an advanced question. I was not planning to discuss phase in this seminar just because we've usually pretty tight on time. I'll just say that the short answer is yes, but that's definitely a person we need to connect with our technical support team.
Okay, I will get their contact information. I've got more in the chat, Dan, but go ahead and proceed and we will answer those questions at the end.
Okay, so I did promise I would explain about weighting filters, and this is the moment we want to talk about it. So let's talk about perhaps the most fundamental measurement, which is signal amplitude. In AP software, but really any time we talk about level measurements, one of the things that we really need to be unambiguous about, oddly enough, is, well, what do we mean? Sometimes we mean, let's take all the energy across all the frequencies that fit in the bandwidth of our analyzer and express the total energy in that signal. That's a very common meaning for a level measurement, and that is what our level and gain measurement does. But our level and gain measurement generally assumes that you're measuring some type of repeating or steady state signal. If we're measuring noise, a true random signal, well, there are a couple things that come in. The first is there is a literally infinite amount of noise in the universe. That is to say, as you increase the bandwidth of your analyzer, you will keep measuring more energy. So when making a measurement of noise, it's important to specify the bandwidth over which that measurement is made. And noise is typically random, so we might want to integrate or average that measurement over an interval of time in order to achieve a nice and repeatable measurement. Finally, exactly, we might want to apply a weighting filter to that signal. And there are a large number of weighting filters. In the lower right, we're looking at a graph of A weighting, B weighting, C weighting, CCIR, CCIT, C message, and this is just a few of them. All these weighting filters are doing is emphasizing or de-emphasizing, so adding or subtracting gain at different frequencies to try and approximate the human hearing response to energy at different frequencies. And you'll see this very commonly when, for example, people will describe the noise level in a building. They might say, oh, in this building, the noise is 60 dBSPL A weighted. So in that case, they literally mean they made a amplitude measurement in that environment. That's dBSPL. But the noise was attenuated with an A weighting curve, which attenuates low frequency sounds and very high frequency sounds, and actually has a little gain in the mid-band because our hearing is actually sort of tuned for the center of sound in human speech. And that's a approximation, a way to provide a score, if you will, for noise that approximates how humans would perceive that loudness. And then finally, sometimes you want to make a level measurement, but over a very defined frequency range. And in that case, we would make a band pass level measurement. So let's take a look at all of these. So first, let's just look at our good old level measurement. So I can go here, generate a sine wave, and let's say I generate that sine wave at 2.83 volts, and this is going into an actual speaker. Now what you're seeing right now is just the ambient noise in this room. I turn my speaker on, and that speaker gives me 103 dBSPL. Now that is a broadband measurement, but since most of the energy contribution was coming from the speaker, it's probably pretty good. Now, if we look at a noise measurement, so now let's say I just want to know how loud is it in this room. So the first thing you notice is that this is jiggling around a bit, partly because I'm talking, but there's other activities going on here. So I might want to go into my advanced settings and set, say, a 2.5 second acquisition time. So this will integrate the measurements for 2.5 seconds at a time. And you notice we get a much steadier response. And exactly now in this case, I might want to say, oh, I want to know how loud it is in this room, but I want it A-weighted. And you notice that the apparent noise level goes down quite a bit once I A-weight it. That is attempting to compensate for the biases in human hearing. Now, finally, let's say I wanted to test the speaker, but at a very low level. It would be a little difficult in this room because the speaker is going to be swamped by the room noise. If I look at my FFT spectrum, I can actually see a little spike here from the output of the speaker, but it's being swamped by all this other ambient noise. Now what I could do here is say, actually, I want to measure the noise within the narrowest band possible, which is called window width, at 1 kilohertz. And now I can actually measure the output level of just that speaker because our measurement is only making a measurement of level just at 1 kilohertz. It's ignoring all the sounds that are adjacent. Okay, I realize we're running short of time, but I just want to cover one more very fundamental measurement, especially in the modern world, which is FFT spectrum analysis. And I've been showing you this as I go, which shows what a fundamental tool it really is. FFT spectrum analysis, as I expect most of you know, is taking advantage of a fantastic mathematical tool, the Fourier transform. And the Fourier transform takes a time domain signal, a sequence of samples, in this case, audio samples, and gives us the representation of the energy as a function of frequency in that sample, in that sample stream. And in fact, today, most audio measurements are made by taking the Fourier transform and summing it up or dividing it up into different blocks and ratioing those blocks. So for example, we could take the Fourier transform of this sine wave. It gives us the spectrum below it. We could sum together all these blocks of energy at different frequencies, and that would give us the total energy in the signal. Or we could say, oh, what's the energy at 1 kilohertz in the fundamental? let's now sum the energy at 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, and so on, which is the harmonics. Let's divide one by the other, and that would give us the distortion. Or let's sum up all the noise and distortion and divide it by the fundamental, and we would get the distortion plus noise ratio. So Fourier analysis is really a very fundamental tool in modern audio analysis. And I won't go into the full depth of it, but I will say a couple of important things. So the first is that in FFT analysis, this is always done on a finite number of audio samples. So you acquire or record audio for a certain amount of time, you gather a certain number of samples, and then you do the mathematical transform on those samples. The frequency resolution is the sample rate divided by the number of samples you've acquired. So just to give you a quick look at what I mean. So right now I'm generating a 1 kilohertz signal, and what's happening here is, even though this is updating continuously, what's really happening is we're acquiring a bunch of samples, we're doing the mathematical transform, graphing it on the screen, and then immediately starting the next one. And that's happening reasonably rapidly. But if I go here and I increase my FFT length, you notice that now I have much higher resolution, but the update rate has gone down. At the other end, I could make this incredibly short, and it will update very quickly. But notice that my 1K signal there is really spread out. I have very low resolution. And there is a 0 hertz function in FFT, and that is bleeding over into the upper frequencies. So there's a trade-off in resolution versus time with our transforms. There are a bunch of different ways in which we can represent the amplitude of the signals analyzed by FFT. By far the most common for audio is what I'll call RMS scaling, or what we call RMS scaling. The other one you will see is spectral density or noise density or amplitude spectral density. The key is this. As I increase let's just do an acquisition of silence, and let's do a really quick FFT. We don't need any delay. So here I did a really short FFT, and below it I did a much longer FFT, and you might say, well, did the noise go down? So this is an RMS scaled FFT, and the key is this: if I am measuring a coherent signal like a sine wave, they will both return the same amplitude. But if I'm measuring noise, the longer the RMS scaled FFT, the lower the amplitude of a sine wave. The lower the amplitude of the noise will appear to be. If I'm measuring noise, and here it's a little bit hard to see, and I use amplitude spectral density, you'll notice that they're sort of about the same amplitude, regardless of the length. The quick and dirty is this: If you're measuring coherent signals, or you want to extract the level amplitude of coherent signals, use RMS scaled FFTs. If you're looking at noise, use amplitude spectral density or spectral density scaled FFTs. Now, the other little detail is both forms of scaling converge when your resolution is 1 Hertz, which is a handy bit of trivia. And of course, what's lovely about an FFT is all the things that you can learn from an FFT. You know, if you have a poor THD plus N, you make that measurement. It doesn't really tell you, you'll just get a number. But if you do an FFT, you can begin to understand, oh, it's because the even harmonics are too high, or there's hum in my product, or any number of other things. Those will pop out of an FFT. Now, I do realize we've gone a little bit over our time, so I'll take this moment and we can just answer questions that have come up so far.
Okay, thank you, Dan. So the first question is a rather broad question about pink noise. The question is, does pink noise have a crest factor? And if so, how does that work?
Yes, all signals have a crest factor. And you know, let's just take a gander. We'll go ahead and generate some noise. Pink. Let's I don't want to. Well, yeah, it should work. Okay, so first let's look at this in the time domain. So here's our pink noise, and the thing that's complicated is in a ideal world, the crest factor of noise is infinite, because if the amplitude of the audio values could theoretically, if you have a random signal generator for a long enough period of time, it will eventually generate a signal, an instantaneous value that is extremely high. In reality, we're generating these signals out of pseudo-random number generators, so there's a finite maximum positive amplitude, but it is quite high. And what you'll see in practice is that noise signals will have high crest factors. Now, sometimes people want to have a signal that has various qualities of a noise-like signal, that is to say, a distribution of energy over frequency that represents random noise, but they don't want a very high crest factor, so they'll apply limiters or compressors or other filtering techniques. But all signals have a crest factor. That one's easy to answer. And noise signals, by definition, will have the highest crest factors of all signal types.
Thank you, Dan. Another question here. Why use a sweep signal instead of each sign frequency to perform THD and HOHD measurements? And what is the advantage of a sweep signal?
So I assume the question relates to using a log chirp, and the answer is very simple. The answer is time. Log chirps or exponential sine sweeps allow us to derive those measurement results very rapidly, usually on the order of 10 times or more faster than a traditional step sine sweep. So I would say it's a practical or a pragmatic reason to do that. In terms of the measurements, there's no you'll get the same measurement results. One will just be faster than the other.
Thank you, Dan. One final question here. Is the sweep continuously accelerating in rate from low to high frequency, or is it a constant rate of low to high frequency?
That's an excellent question. It is accelerating, and that's what the log in log chirp refers to. So there is an older technique that is a linear continuous sweep where the rate change of frequency with time is constant. The improvement that's been made since then is that mathematically, if you sweep continuously but accelerate at an exponential rate, there's some very interesting things that happen when you do the mathematical transform that allow you to extract the THD data. So it is, yes, and it's the log part in log chirp refers to the fact that it's an exponentially increasing rate of change in the frequency with time.
Great, thanks, Dan. That concludes the Q&A.
Find out more at Vicom's website.